lexicographic order. But the problem is little different. Here, earlier what we decided? We have the n elements. The elements are distinct and you have selected R of them, or you have arranged using R elements. That means you have the number of permutations is NPR. Right? Now what happens that if these elements are not distinct, these n elements are not distinct, right? Then how to generate the foundation of R elements out of N? So let us assume that there are k kinds of objects, k kinds of objects, right? And first kind, there are R1 object. Second kind, you have R2 objects, and kth kind, you have Rk objects. So that summation over Ri is R. Sorry, is N. Summation of Ri is N. So what is given? There are n objects. The objects are not distinct. The objects are of k kinds. First kind of R1 elements, second kind of R2 elements, and kth kind of Rk elements. So that means the total of this R1 plus R2 plus Rk must be equals to N. Now you have to select R elements, or not R select. You have to make the arrangements of R elements out of these N elements. So that if N0 is the total number of such permutations, then I can write a different notation I should have. R0, sorry, R1, R2, Rn. This is nothing but n factorial, R1 factorial, R2 factorial, Rn factorial. Right? And this can be written as n by Ri, n minus 1, R1, R2, Ri, minus 1, Rn. Okay? So, N0 is the total number of permutations, N0, R1, R2, Rn. So, n factorial, R1 factorial, R2 factorial, Rn factorial. And this can be defined by R by n by Ri, n minus 1, and R1, R2, Ri minus 1, Rn factorial, Rn. Right? Just I have taken out Ri from one Ri from here, so it has come Ri minus 1. Now, suppose N is the number of permutations where first m elements are known. Right? So I can write n minus m and R1 minus T1, R2 minus T2, this must be K, right? Rk. Rk minus Tk. So this is the total number of permutations you have, where first m elements are known, and these m elements consisting of T1 of first kind, T2 of the second kind, and Tk of the kth kind. Right? So this I can write n minus m Ri minus Ti also I can write here n minus m minus 1 R1 minus T1 Ri minus Ti minus 1 Rk minus Tk. This I can write just from the same way. I can also write Ri minus Ti n minus m n of so I can write from here. So this is nothing but I can write n minus m Ri minus Ti n of m plus 1. Right? So n of m plus 1 is equals to Ri minus Ti by n minus m n. So what it gives, that if I know the first m elements where T1 of first kind, T2 of second kind and Tk of kth kind, then this many permutations you have whose m plus 1th element is I. This many permutations you have whose m plus 1th element is I. Is it okay? So this gives you the number of elements of number of permutations of an m whose m plus 1th element is I. So given n0, you have obtained an m set. Right? So nm is the number of permutations whose first elements are defined. A0, A1, A2, An. Now you are thinking how to generate the m plus 1 element so that the elements are in lexicographic order. Now these nm permutations can be numbered from 1, 2, 3 up to nm, right? Because there are many permutations whose first m elements are fixed, and this can be numbered 1 to nm. Now 1, 2 R1 minus P1 by n minus m nm. So these are numbered, these permutations are numbered 1 to nm. Now 1 to R1 minus P1 by n minus m nm. That many permutations whose mth element is 1, m plus 1th element is 1, because they are in lexicographic order. 1 to R1 minus P1 divided by n minus m nm. That many m plus 1th element will be object 1, first kind. Now R1 minus P1 n minus m nm plus 1 dot dot R1 minus P1 n minus m nm plus R2 minus T2 n minus m nm. This will give you the object of type 2. Similarly, if I go further, summation over Ri minus Pi or Rj minus Pj n minus m nm plus 1 j is 1 to k minus 1. So this will be of object K, right? And I want to arrange them in lexicographic order. So since I want to arrange them, so this will be obeying the thing. Now more clearly, I can define an array SM0 is 0 and SM J is equals to Sm j minus 1, or I can put I plus Ri minus Pi n minus m n. I can define a reconciliation Smi is equals to S of I minus 1 plus Ri minus Pi n minus m n. Right? Just the summation sign I am replacing, nothing else. And I can be 1, 2, up to k, because there are k kinds of objects. So from this, no, this I should put 0, otherwise you are in problem. So from this I can derive a relationship Sm0 less than equals to S of M1 Sm0 less than equals to Sm1 less than, because these are all positive numbers, less than equals to Smk, and Smk is nothing but the total number, which is Nm. Now come back to our gamma permutation. I have X gamma whose first m elements are known, A1, A2, Am. I have to find out the m plus 1th element. Now in the sequence there will be several such, there will be Nm permutations whose first m elements are, say, A1, A2, Am. And gamma is also having the first m element, so gamma must belongs to this one. So let us assume that delta gamma m is the index of X gamma in this lexicography index of X gamma in this Nm. So delta must be lying between Nm, right? Delta is lying between 1 and Nm, and this S also lying between 1 to N. Now I have to arrange, since I have to arrange in lexicographic order, I have to look for an I in this sequence such that S of m I minus 1 less than delta that means I am looking for a smallest I such that S of I minus 1 less than delta gamma m less than equals to S of mi. And that I is the object you are selecting as an m plus 1th element for X gamma. Now clearly, since this is lying between 0 to Nm, this is also lying between 0 to Nm, such an I must exist. because this is lying within the range. So and moreover, since this is an increasing order, so you can use the binary search to find such an I. So if it is that case, then I can have an algorithm to generate X gamma. So initially your gamma is delta, right? So I have to obtain the gamma Lec-21 product, and your N0 is the total number of permutations. This is you have computed R1, R2, Rk. Now you have to find out for n equals to 1 to R, that R elements you have to find. So first you have to define what is your SM. SM0 is 0. S of M I is equals to S of M I minus 1 plus Ri minus Pi n minus L n minus 1. So this is, you have to find the value of SM. Now once SM is known, for I equals to here, for I equals to 1 to k. Now you have to find out, find a j or find a I. Find a I in Sn such that S of M I minus 1 less than delta less than or equals to S of M I. Right? That I is important, and that I is your result. S of A of M is your I. Now once M is defined, now you have to modify the value of Nm. What will be the value of Nm? Value of Nm is nothing but Ri minus Pi divided by n minus m, n of m minus 1. Right? So this Nm will be used for the next iteration. Then what is the value of delta? Actually, this can be, I don't have to compute this, I can straight away get it. Nm is equals to S of M I minus S of M I minus 1. That will give you straight away. And what is the value of delta? Delta is delta minus S of M I minus 1. That will give you the position of delta for the next iteration. So anything else you need? Oh, you need now the value of I you have selected. So Ri is reduced by 1. Because Ri is now size, or basically Ti is increased by 1. Either you increase Ti is increased by 1. So the next time, best way that I should use Ti is increased by 1. Anything else? No. So everything is taken care. This is your algorithm to generate R elements of lexicographic gammite permutation. So you observe that it is an independent in nature, so it is straightforward and an RFP algorithm you can write. So suppose I have NPR processors, not NPR, N0 processors, the total processors you have, then you need order R time, am I right? For these iterations. Yes. No, because n is 1 to 1. Now observe, there is an addition is in between. So that addition is of size k. So order R into order k. And rest of the thing, this is plus order log k. This is a binary search, so order log k. So the complexity becomes, if I have N0 processors, then order R into k, because this is log k comes much less compared to order k, so it is order R into k. Now, but since this can be written in an adaptive manner, so I can have, suppose I have P processor, then the time complexity becomes order n P R into K. Right? Now you can improve the time complexity further by increasing the number of processors. Basically, what happens? Let us go back to our initial or finding the sum of n numbers using, first we tried with using n processors, right? So what happens? I have x1, x2, x3, x4, x5, x6. Suppose there are 8 numbers and I have the n by 2 processors, right? What I did, sum of n numbers, I divided into 4 groups. Each group is having 2 elements and I just add them. So I get x1 plus x2, I get x3 plus x4, I get x5 plus x6, I get x7 plus x8. Right? So this is one iteration. Then I divide into 2 groups, and instead of 4 processors, now I am using only 2 processors. I add these 2, I get sum of first 4 elements and I get sum of next 4 elements, which is another parallel steps unit. Now one processor I am employing and add this, so I get the sum of 8 terms. So you need log n iterations, log n additions to find the sum of 8 elements. This log n parallel additions, remember, do not confuse with the parallel and sequential, because sequential addition is, number of sequential addition is n minus 1, but number of parallel addition is 3 using 4 processors. You observe that at every stage I am discarding 50% of the active processors. Right? So first I use 4, then the 2 processors, and then 1 processors. So if I see in terms of n, if you have n elements, then you need order log n additions to find the sum of n numbers. And the cost is becoming order n log n. Right? This into this order n log n. which is not a cost optimal algorithm. So you remember that what we discussed to make a cost optimal algorithm, I divided this n element into n by log n groups. N by log n groups. And each group is of size log n. Okay? N by log n groups, each group is of size n by log n. The size log n. And I employ n by log n process. That many processes I employ. Each process is attached to one group. And it finds the sum of these elements, right? Sum of these elements, which is x1, sum of this element x2, sum of this element is xn. Xn by log n, n by log n, right? So now you have n by log n elements and you have n by log n processor, you follow the same thing, same way. You will be getting the sum of all these things, in order n by log n time, log of n by log n time. And also, you did the sequential addition which was taking log n time. So order log of n by log n plus log n time, right? So this I can write order log n minus log n, right? Or order log n time. Now you observe that cost of this algorithm is order n by log n into log n, which is order n time, which is cost optimal, right? So that I discussed in earlier class, in one of the earlier classes, that you can have cost optimal algorithms to find the sum of n numbers. So same idea. Suppose I use simple thing. I use k processors to make it. There are k elements, k things you have to compute, SM0, SM1, SM2, SMk. I employ k processors. So log k time is sufficient. Log k time is sufficient to give you the sum of k elements. So if I employ pk processors total, and for each permutation I give k processors, right? In that case the time complexity becomes N0 by P into R log k time, right? Because by k processors I generate one permutations. So if I employ kp processors, then I will be generating p permutations at a time, right? So total number of iterations required order N0 by P is the total number of iterations, and at each iterations you need R log k. Obviously, this is not cost optimal, but it is very simple to use it, not that much difficult, right? Is it okay? So this is about your permutation algorithms. Let us see an example. Suppose I have n equals to 4, R1 equals to 2, R2 equals to 1, and R3 equals to 1. That means there are 4 objects, 3 kinds of objects, and 2 of first kind, 1 of second kind, and 3 is a third, 1 is of third kind. So K is 3. What is your N0? R1, R2, R3, which is 4 factorial, 2 factorial, 1 factorial, 1 factorial. It is 12. What are those 12 elements you have? First, let us see 1, 2, 3, 4, 5, 6. So this permutation, let us understand lexical permutation is 1, 1, 2, 3 is the first combination, then 1, 1, 3, 2, then 1, 2, 1, 3, then 1, 2, 3, 1, then 1, 3, 1, 2, and then 1, 3, 2, 1. You have 2, 1, 1, 3, 2, 1, 3, 1. 2, 3, 1, 1, 3, 1, 1, 2, 3, 1, 2, 1, and 3, 2, 1, 1. So these are the 12 permutations you have. So let us assume there are 12 cross sets you have. So you have N0 is 12. And number of cross-sets is 12. Say, what happens? 7 permutation, what it generates. So you have delta is equals to 7. Now, so you have delta, you have M, you need to generate S SM1, SM2, SM3, because 3 kinds, you need to generate that. Then you need to generate what is your AM, then your NM, and then delta value, and then T value. Delta is, your NM is here somewhere, right? In here. Delta is 7, M is 1. Here I put NM minus 1. And this is 12. Right? What is SM value? SM1? SM1 is R1 minus T1. R1 minus T1, T1 initially is 0, and N is what? 4 minus M is 1, so 3, NM minus 1, NM minus 1 is 12. Tell me, what should the value? R1 is 2. This 6, right? R1 is 2, 3, and 4, 40, 6 or 8. N minus M, M is 1. No. This should not be N minus, then I should start with 0, right? N minus, because Ti is, I have to get 6. I have to get 6 because first element is 1, 6 of them. So this must be m minus 1, this must be m minus 1. And here I have to write these are zeros. This is n minus 1. So it is R1, 2 and 6. This is 6. Now what about R2? R2 is 1. 1 by 4 into 12. So it is 3 plus 6. So it is 3 plus 6 is 9. And here it is 9 plus 3, because this is also again 1, or 3 is 1. So it is 12. So you observe here there are 6 ones. First element is 1, that is the 6. Then 3, first element is 2, that is your 3. And 3, first element is 3, is 3. Now you have to find out an I such that 7 lies in that. So 6 and 9, so 7 lies here. So AM is 2. Okay. Now what is your NM? NM is that this minus this, S2 minus S1, which is 3. Delta E is 1. 7 minus 6 is 1. T1, T value 1 is increased by 1, which is 1 now. T value increased by 1, so it is 1. So delta is 1, M is 2, what is NM? NM 1. NM 1 is 3. What is now SM1? SM1 is R1. R1 is now R1 minus T1. That means 1. 1 by N is 4. M minus 1 is 1. And this is 3. NM is 3. So it is 1. So this is 1. Right? Now what is SM2? SM2 is also 1. SM3 is also 1. So 1 plus 1, it is 2. And 2 plus 1, it is 3. And if you compare, then it is lying here. Right? So AM is 1. And NM is 1. Delta is 1. T1 is now 2. Right? Hey, AM is 2, no? So it is T2 is increased by 1. So I made mistake I think here. T2 is increased. T2 is increased by 1. Have to do some work here. So this calculation will be wrong. R1 is 2 minus 0. N is 4. M is 2 minus 1 into NM. NM is what? NM minus 1 is 3. Then this is coming this. So this is 2. So this is 2. And this will become 2 again, because R2 is 1, 1 minus 1, so it is 0. So R2 plus this is 0, and this will become 3. AM is now 1, 1 is this, so AM is 1, NM is, what is the value of NM? Now, Nm is this minus, so Nm is 2, right? Delta is 1, and here T1 is 1. T1 is 1. Delta is 1, Nm is 3, Nm minus 1 is 2. What is SM1? SM1 is R1. R1 is 2 minus 1 is 1, and N is 4 minus M is 3 plus 1. 3 minus 1, sorry. 3 minus 1, and here it is 2. So 4, and here it is 2 cancel 1. So this is 1. There is nothing in SM2 is 1, and SM3, 1 plus 1 is 2. Because there are how many elements? Let us consider. R3 is 1, 4 minus 3 minus 1 into 2, so this is also 1. 1 plus 1 is 2. So now 1 you will be comparing, so this will be the first elements 1. Nm is what? Nm becomes again 1, because this minus this is 1, delta is 1, and T1 is increased. Now T1 is achieved at T1. And then it is 1, M is 4. R is 4. 4, Nm minus 1 is 1, and this is 0. So this is 0, this is 1, and the resultant will be this one is 3, and rest is not required because 4 elements to be generated. So result will be 2, 1, 1, 3. So that is your 2, 1, 1, 3. Right? Generation of combination in lexicographic order. Right? And you know what is combination. Combination is nothing but the selection of odd elements out of n elements. Alright? So suppose I have n equals to 5 and r equals to 3, then there are how many combinations you have? 10 combinations you have. And suppose these 5 numbers are 1, 2, 3, 4, 5, then the combinations are 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, 1, 4, 5, then you have 2, 3, 4, 2, 3, 5, 2, 4, 5, 3, 4, 5. Right? This is a lexicographic order. So by lexicographic order I mean you see that this is in increasing order and this is also in increasing order. Right? 1, 2, 3, 4, 1, 2, 4, 1, this is in increasing order, and this is another, and also that ith permutation, ith combination is lexicographically precedes the I plus 1th combination. Right? Because in the case of combination, one thing is that 1, 2, 3 and 1, 3, 2, they are all same. Right? Occurrence of elements doesn't make sense in the case of combinations. So here what we did in the case of lexicography, that we take that part arrangement where the elements are in increasing order. That is the idea. Now in the case of a combination generation, what we do, given ith combination, I want to generate I plus 1th lexicographic combination. So if I have ith combination, right, A1, A2, AR, can I generate my next lexicographic combination from this? That is the problem. If I can do it, the problem is solved. Now one thing you remember, that first combination of R elements, first lexicographic combination of R element is, right? This is the first part, that 1, 2, 3, here 1, 2 up to R. And can I find out what is my last combination? Last combination must be right? This is my last combination. So this is the first combination, this is the last combination. Last lexicographic combination. That is 3, 4, 5. Here it is. N is 5 minus 3. 5 minus 3 is 2. 2 plus 1 is 3. 3, 4, 5. Now can I find out what is the minimum? Suppose this is the ith element. Ith element. Now this ith element, what is the minimum value? Minimum value is I. What is the maximum value? It can retain. Can I find out? What is the maximum value it can take? Ith position. Nth position, rth position is n. Maximum value it can take n. Ith position?
Minus I.
N minus?
N minus I minus 1.
I?
N minus I.
I minus I plus what?
Plus N minus
Right? Is it? Now if, what is the maximum value of R can take? This rth position? It can take n. Ith position?
N minus I plus 1. That is the I condition.
See, one thing remember, if this is I, next element will be I plus 1 onwards. It is always increasing order. Right? Suppose this is n minus I plus 1, then this will be plus 2, this will be. If ith position is n minus I plus 1, I plus 1 is position, it is n minus I plus 2. Right? Rth position it will be R I plus R minus I is your, right, and this is equals to n I is minus I plus R
Minus I plus 1.
minus I. Minus I
plus 1.
plus 1 plus 1. So what is the value? It is n plus R plus 1. It can take maximum n. Yes or no? This can take maximum n. So what will be the value here? This is n minus 1. Here it is.
R minus I plus 1.
R
R minus I plus 1.
n minus
R minus I.
R plus I.
R minus I plus
R minus 1.
R minus.
R, it should be in terms of n. Because it is n minus 1. So when I equals to r, then it is n
minus r
plus I.
plus I minus 1.
Why minus 1 is coming? When I equals to r, maximum value is n. So n minus r plus I. So the maximum value of I at location is n minus r plus I. Right? Minimum value is I, maximum value is n minus r plus I. This is known now. Now the thing is that suppose I have a combination of R elements. If this last element is not n, I can get easily the next lexicographic one just by adding 1 here. Right? Suppose it is 1, 2, 3, 4 up to 3 and this is not attained the maximum, it is maximum is 5. If it is not maximum, just I add 1, I get the next combination. This is not maximum, I add 1, I get the next one. The first one is clear, that if the rth element does not reach to the maximum one, I can get the next combination by adding 1. Now, suppose that ith element has attained its maximum, right? What it means? That this value is n minus r plus I. It has attained its maximum, ith position. Remember that if ith position attains its maximum, the next all elements also attain their maximum. That this is maximum, this is maximum, this is maximum, this is maximum. If this is maximum, then all of them are maximum. Because this is increasing order and one short of the previous one. So if it has attained maximum, then this will be attaining maximum, this will be attaining maximum and so on. What it means that this has not attained its maximum. Just previous element, I minus 1th element has not attained its maximum. Am I right? But ith element has attained maximum. This onwards everybody got the maximum, but this is not maximum. So if this is not maximum, I can generate the next permutation just by adding 1 here, by adding 2 here, by adding remaining. So this plus 1, this plus 2, this plus 6 and so on. So that will give you the increasing order of combination, right? So if I know I minus 1th location's value, I can add all of them to get the next one. The formula is xi is equals to, or let us put yj is equals to xj and j is equals to 1, 2. Same thing I will be retaining I minus 2 and yj is equals to x of I minus 1 plus j minus I plus 1 for j I minus 1 onwards. X, what is the formula I am writing? That suppose this has attained its maximum, this has not attained its maximum, then this value, up to this I will be retaining same. This one onwards I have to change it. That is, I am writing the same, that is nothing but yj is equals to xj, same for this region. For this region, yj is equals to x of I minus 1 plus j minus I plus 1. So, in the case of I minus 1, it is not plus 1, plus 2 should be. Because in case of I minus 1, this gives you what? J is I minus 1. J is equals to I minus 1. So this gives you minus 1. So just adding 1 to the I minus 1 position. When j equals to I, then whatever number I got plus 1, plus 2, plus 3 and so on. Right? Now let us define few arrays first. Otherwise it will be difficult to write the arrow. I know one array is max. That means maximum value it can attain. So what is your max I? Max I. Max I is n plus n plus r, n minus r plus I. Right? And I equals to, am I right? 1 to r. When I equals to 1, it can take n minus, just I have obtained n minus r plus I. N minus r plus 1. N minus r plus, when r equals to r, then it can take this. Then I need to define a current status of my combination. So that from there I will be detailing, I will be understanding whether any position, whether it has attained its maximum or not. So current I is a current combination. Final I is the array to print the combination. To print a combination. And then you have logical I. Logical I, it is the ith element, a logical array I am introducing, ith element, whether it is attained its maximum or not. If it is maximum, then you write false, otherwise it is true. Then you write true, otherwise it is false. It is true if current I is equals to max I. That means current position has attained its maximum, and if current I is not equals to max I. Right, so these 4 arrays I need to design my algorithm. So initially max I equals to n minus r plus I. Current I is I. Right? With 1, 2, 3, 4, 5, 6, 7, 8 up to R. And this also will be a final result because you have to print once, so I. And logical I, you have to check. So logical I, in order to check it for I equals to 1 to R, if max I is equals to current I, then logical I is true, else logical I is false. So logical I is also defined. Now if logical I minus 1 is not equals to logical of R, what it means? If logical I minus 1 is not equals to logical I, you remember one thing, that true comes from the right to the left. False is always at the left. Because I am always adjusting at the end. right, of the combination. So logical I minus 1 is not equal to logical I. It means you got several false, then here it is true, 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 and so on. So this is I minus 1 and this is I. Right? That means ith position onwards you got your maximum. So if logical I minus 1 is not equal to logical I, then you can define your current new I, current I, or not current I, current J, let me write. Current J is equals to current of I minus 1 plus J minus I plus 2. Right? For all J greater than equals to I minus 1. So current J I will be defining now, but just I have obtained this formula. Next one is, if there does not exist logical I minus 1 not equals to logical of I. If there does not exist any such, then what does it mean? That means you did not get a condition where you have false, 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 and then T. You did not get such a condition. Right? That means this is also false. That means the last element has also not attained its maximum. So in that case, I can always write current of R is increased by current of R plus 1. Just I increase it. Right? So in that case, combining these two, can I write current of I is equals to, or current of J is equals to current of I plus J minus I plus 2 for J greater than equals to I minus 1. I have to define now what is J, what is I. I is, just I am combining the result. J if logical K minus 1 is not equals to logical of K and R plus 1 otherwise. Basically, I have used these two statements to define the new one. That's good. So what happens, given a sequence or given a combination, I just check based on my logical statement and current statement, I can get the next one, which will be my final. Right? So which I will tell, then generate, given a combination, generate current, right, based on this, and then your final is your current or print current or print final, and then you have to update your logical one. So if for I equals to 1 to R, if current I is equals to max of I, then logical I is true, else false. Right? So this will give you a whole algorithm that given a combination, you can easily obtain what is my next lexicographic combination. Now, if I have R processors, so for each of them, this is if I know one processor for allocated to one element, R elements. So R processors for to generate R elements, right? So everybody looks about his ith processor checks his position of ith element. So constant time is required to generate next combinations, right? And since there are NCR combinations, so you need NCR time to generate NCR combination using an R processor. It is not cost optimal, right? Is it okay? I think this is very simple, but then also for completeness sake, let us consider one example. Suppose I have n equals to 5 and r equals to 3. N equals to 5 and r equals to 3. We have 10 such combinations. Now, I wrote somewhere. Let us assume that I have current, right? I have final, I have logical. Now, say let us assume that 1, 3, 5 is my current one. So this is printed 1, 3, 5. Now 5 has attained its maximum, right? So it is false, false, true, right? Now what I am generating my current is nothing but that once this is different, this is same, right? So no change here. This is different, then this will be incremented by 1 and the next element will be added by 1, that is 4, 5. This plus 1. Right? Instead of added by 1, what we did, this element will be read, this will be read by each processor, this will be added with j minus I plus 2 form. So everybody can compute j minus I plus 2 and add with this value. So this takes order 1 time. So but only issue is here that each processor must be able to read a location simultaneously. So concurrent read should be happening. Okay. So this is all about your combinations. Okay. Thank you.